All right. Good afternoon, everyone. It's my pleasure to introduce our colloquium speaker this week, Dr. Drew Newman. Drew did his undergraduate studies at Washington University in St. Louis before he joined the department here as a graduate student over a decade ago. He worked primarily with Richard Ellis on the formation and evolution of massive galaxies and clusters. And then following his graduation in 2013, right? 2013, he joined Carnegie Observatories as a Carnegie Princeton Fellow, and he was there for a couple of years before they realized the brilliant scientist that he was, and they hired him on as a staff scientist, where he's remained since then. And he also has a joint appointment at USC, where he can advise students. So Drew has made a bunch of different contributions in different areas, but I think most of his major significant contributions were made in massive galaxy and cluster halo evolution and studies of the relationship between quenching mechanisms and environment and chemical evolution, chemical abundances in the stars and dynamics. He's also looked at dark matter halos and the relationship between their radial profiles and the baryons and over a variety of different cluster masses, halo masses from clusters down to dwarfs. And then more recently, he's gotten really involved in this research with looking at the cosmic web and the distribution of matter on large scales and potentially being able to probe this directly with Lyman-alpha tomography. So take it from there. Thanks.
Thank you very much, Cameron, and thanks to you all for the introduction. It's really been a delightful day to kind of come back and meet with some of you. What I thought I would spend this colloquium talking about is a project that I started about 5 years ago using the Magellan telescopes in Chile that Carnegie operates. And the goal of this project was to start making maps of the cosmic web around redshifts of 2 to 3 using a fairly new technique called IGM Tomography that I think is really exciting. And this survey that we've undertaken is enabled by the efforts of a lot of people. I want to highlight particularly Gwen and Guillermo Blanc, Nima Chartib, who's here in the audience, is a postdoc at Carnegie now, and Maddie Kezlu, who's a graduate student at UC Riverside, one of our Carnegie UCR graduate fellows. The overarching question that kind of led us into this project was how does a galaxy's place in the cosmic web influence its evolution? So this is kind of a broad question, but it's just one aspect of what is commonly referred to now as the baryon cycle. So this is the exchange of material within galaxies and with their surroundings, and it's very multi-scale. So it reaches from the very centers of galaxies and the supermassive black holes to the scales of giant molecular clouds and galaxy disks. Those disks are profoundly affected by accretion and feedback from star formation. They exchange material on kind of 100 kiloparsec scales with the so-called circumgalactic medium, a big focus of research now. But then all of this material ultimately is, of course, coming from the cosmic web on large scales, and this has structure well beyond the size of the individual galaxies that are growing within it. So that's going to be my main focus is how does this kind of large-scale region around a growing galaxy affect its development. This is generally called the environment, which has a lot of different meanings depending on what you're trying to do. But broadly, we're just trying to get some measure of the surroundings of a galaxy on scales well beyond the galaxy itself. Usually we're trying to get at the matter over density. And this is definitely important if you think of what might be called data-driven descriptions of galaxy properties and how they vary. Environment's usually the number 2 parameter behind a galaxy's mass and describing how galaxy properties vary. And the reason for that, I think, is that it's kind of an accessible proxy, something we can measure for a number of different quantities that are clearly important for in models of galaxy evolution. So all of the gas is ultimately coming from large scales funneling into galaxies. The anisotropy in the cosmic web is the source of angular momentum, which is a really important parameter in galaxy formation. Dark matter halos collapse at different times in different large-scale regions, so the clock kind of statistically starts differently in a sense for galaxy evolution in over and under dense regions of the universe. Galaxies can be profoundly affected by interactions with gas, so if they fall into a more massive halo. They can be kind of disconnected from their gas supply. They may even have their ISM swept out as they fly through that halo. That, of course, depends on the environment. And galaxies can interact with one another, for instance, via mergers and other processes that depend on the environment. So we kind of know all of this happens, but don't really have a very clear picture of how all of these things act to produce the observed galaxy population. And so I think observationally, one tack we can take is to try to map out when galaxies and their properties started to depend on the kind of large-scale environment. Some of these things we expect to happen from the beginning, some of them to occur late, they occur on different timescales and so on. So it's nice to have some look-back studies to see when this happened. And in order to do that, we have to have, of course, maps of the cosmic web over a variety of look-back times. You're all familiar with maps like this of the local universe that have been assembled by galaxy surveys over the years, exquisite detail. As we go back in redshift, back to, say, redshift 0.5 to 1 or so, this has really exploded recently, driven by really cosmology experiments on 4-meter class telescopes. It's exploded in terms of the volume. So we have very large volumes. In terms of kind of map quality, which depends on the density of the galaxies that you're measuring, that's still kind of state-of-the-art with surveys on 8-meter class telescopes. But then as we go back further to the so-called cosmic noon era, around redshift 2 or 3, it's a dramatically different situation. The biggest surveys are like a few thousand galaxies over square degree areas, and this is all on 8-meter class telescopes. Just to give you a kind of visualization of what that looks like in terms of cosmic web maps. This is a panel showing a simulation, the dark matter in a simulation on the left, and then how that would be sampled by kind of a state-of-the-art galaxy survey in the nearest few hundred megaparsecs, for instance. You can clearly trace out lots of features in the cosmic web really nicely. As you go back to redshift 1 or so, it's actually still pretty good with the advent of some of the more recent surveys. But then when you go back to redshift 2 to 3, first, the cosmic web itself is less developed. All of the kind of density contrasts are lower at those early cosmic epochs. And then the sampling by galaxies is much sparser. So it becomes very difficult to map out the cosmic web. It's not impossible, certainly, and important work has been done. If you kind of step back and take a smooth version of this and look how the galaxies trace the density field, you can pick out like the larger scale modes in the density field with galaxy surveys. It's not impossible, but we're definitely in a very data-starved regime as we go beyond redshift 1.5 or 2. So what can we do to improve this situation, make better maps of the cosmic web to learn about galaxy growth and for cosmology as well? There's several strategies that you can imagine. So one is to say, okay, let's not just make kind of contiguous maps of a blind volume. Let's find certain areas that seem, for instance, to be very rich in galaxies, and then do targeted follow-up of those. And this is a widely applied method. You can either choose kind of normal galaxies in kind of optical infrared surveys. This is an example in the cosmos field where you see a big overdensity identified by photometric redshift technique to localize them along the line of sight. This is another tactic is to, instead of focusing on kind of garden variety galaxies, to look at more rare populations that might be kind of signposts for big overdense regions. That can be far infrared or submillimeter or radio bright galaxies, for instance. And this is also a technique that's been successful in identifying kind of special environments in the distant universe. This is an example of galaxies around a radio loud source at redshift of about 2. So both of these are successful, but you don't really pick out the whole kind of population of structures. You're looking for, in this case, specific galaxies with short-lived phases in some cases. And in this case, the main problem is that you don't have very good information about the distance to the galaxies, and so everything is severely blurred along the line of sight. So spectroscopy is preferable for that technique. One strategy to get better maps of large-scale structure at high redshifts is just to go much wider, and that is definitely on the horizon with projects like PFS that many of you, I guess, are familiar with, and from space with Euclid and Roman soon. So those will give humongous volumes with kind of with pretty good density, but not dramatically higher density than I think we can do now. If you want to get much more detailed maps of the large-scale structure, then your only choice is to go much denser, and that requires going much deeper to identify fainter galaxies. And that can be done now over small volumes with JWST, and over larger volumes it'll be possible with the extremely large telescopes. But for now, what can we do? Another way is to just take a completely different approach, and instead of mapping out the large-scale structure with galaxy surveys, is to use a different tracer. And one such promising tracer is to instead make maps of the intergalactic medium. And this brings me to the technique of IGM tomography that we've implemented in the survey that I'll describe. So the large-scale structure, is commonly visualized in dark matter simulations like this one, but of course it's also pervaded by the IGM, and on scales that are above a few hundred kiloparsecs, the distribution of the hydrogen tracks the matter distribution basically. And so you can use this because a small fraction, of course, is neutral and is therefore observable in the Lyman-alpha transition, making it more accessible to observations. So in dense regions of the IGM, you can detect emission from Lyman-alpha. This is really just kind of starting to be done over the last 5 years or so in a large scale with the advent of IFUs like KCWI and MUSE. This is a really nice example of these few filaments that seem to be converging on the structure around redshift 2.7, I think. And of course, the intergalactic gas can also be detected by the absorption that it imprints on spectra of background sources. And classically, this is studied by quasar absorption line spectroscopy, which has a long, distinguished history here, so maybe not much description is needed, but you can see in this example, the Lyman-alpha forest, all these absorption lines arising from H1 in the IGM are being imprinted on the spectrum of this quasar. This gives you really exquisite information, but it's confined to a single line of sight, of course, in this example. So if you want to build up 3D maps of the intergalactic medium, then you need to observe many sight lines. This is what's generally referred to as IGM tomography. So if you have many different sight lines towards some background sources that pierce the same volume, then you can kind of interpolate between those and build up maps of the IGM. The backlights could be quasars. This example illustrates that. All of these sight lines have kind of a density representative of a quasar survey. This is just a cross-section of this simulated volume, so you can see the dots are the sight lines. This can be done. It has been done. The main problem is that they're just so sparse. So you can see even the biggest features in the density field you might just miss because there didn't happen to be a quasar behind them. So if you want to go to much finer sampling, pick out kind of more detailed structure of the cosmic web, then you have to get a lot more sight lines, and the only possibility is to go to much fainter sources. And you can do that by instead observing bright Lyman break galaxies. So it's much more difficult because they're fainter, but you have about 30 times more sight lines. And so now the typical separation between your sight lines, which if you think about it, it's kind of the smallest scale that you can hope to have any information on in your maps, this now gets pushed down to a few co-moving megaparsecs. And that's an interesting scale, as you'll see, because it's kind of the size of some of the larger features we expect to be present in the density field at this epoch. The kind of concepts and some of the mathematical techniques for this were originated in the early 2000s by Pichon and Kochi and collaborators. What I think of as a high-fidelity version of this is a key science driver, actually, in many of the galaxy evolution science cases for the ELTs. That envisions really high density of sight lines that accesses scales comparable to the circumgalactic medium of galaxies. I'll mention this at the end. But what K.G. Lee pointed out in this really interesting paper in 2014 was that we could already make some progress along those lines with current facilities, and that it should be possible to get enough sight lines toward luminous galaxies to map out the cosmic web at a useful resolution. This is from that paper. You can see kind of a simulated Lyman-alpha absorption field, so the red regions here are the overdensities with more absorption, and then how that might be reconstructed with some notional surveys on kind of 8-meter class telescopes. So it looks pretty good in some of these examples, and that was pretty inspiring. The reason that, well, there are several reasons why I think this is a useful technique. One thing is that anytime you're doing a galaxy survey, you're probably observing the Lyman-alpha forest if it's an optical survey of many galaxies anyway. So there's kind of information in there that you already have that you should be using. Another nice thing is that you get, every galaxy now is not only telling you about its immediate surroundings, it's telling you about the matter distribution for several hundred megaparsecs in front of it. So even if you have a really kind of junky spectrum, which is basically the case, as you'll see, that's a lot of information averaged over many sight lines. And the thing that I think is the most exciting about this is it provides a way to trace the cosmic web that doesn't depend on the galaxies within any of the structures you're finding. So this is important because we don't, as you'll see, have like complete galaxy surveys at these redshifts. So we know there's populations that we hardly have any redshifts for. So if those are inhabiting certain regions, like big overdensities, then they can be hard to find. With IGM tomography, you can in principle find a big matter overdensity, even if you're not capable of, in principle, of getting any spectroscopic redshifts of any of the galaxies within it, which I think is pretty interesting and complementary to the usual galaxy surveys. This has applications for cosmology I'm not going to talk about because you need a way bigger volume, but also mapping galaxy environments. So what might we expect to actually be able to do? These are some simulations by Matti Keslu. So this is showing a dark matter, a slice through a simulation of the dark matter density, smoothed. The middle panel shows what's called the Lyman-alpha flux, so the red regions here where there's more Lyman-alpha absorption. And then this is kind of a mock reconstruction of what a realistic survey, like the one I'm about to describe, could actually do now. And the correspondence is like, it's pretty good on the large scales, considering that this is redshift of 2.5. So that's pretty exciting. And the other thing that's interesting about having these maps, besides locating and kind of tracing out the positions of over-dense and under-dense regions, is that you can estimate their masses. Usually this is tremendously hard to do for structures at high redshift. They're not virialized yet. You don't have like really massive collapsed halos. But with IGM tomography, you can get a pretty decent handle. So what you see in these plots is, on the horizontal axis, what we call the tomographic mass. It's basically a number you can get by like integrating out the absorption that you just saw on those maps and converting this to a mass estimate. And then on the vertical axis, in these mock surveys in the simulation, you see the corresponding dark matter mass. So it kind of depends on what volume you're trying to weigh. If you define it in advance, like a sphere of a certain radius, you want to know what the matter density is, you can actually do that really well with current generation IGM tomography surveys, which is pretty cool. It gets a little harder if you want to let the data tell you what a structure is and integrate the mass within some like isodensity contour or something. That's more challenging, but still actually pretty useful considering how imprecise our mass estimates usually are. And in terms of like what we're actually able to detect, you can see all the masses here are above 10 to the 14 silver masses. It turns out that this is pretty close to the collapsed mass at redshift 0. And so what that means is what we're really sensitive to with current IGM tomography experiments is the progenitors of galaxy clusters, which are called protoclusters. Let me say just a little bit about these. So there are various definitions, but a popular one is that a protocluster is just a region that's going to become a galaxy cluster. So this is a volume that will form a halo of above 10 to the 14 silver masses by redshift of 0. When we call it a protocluster instead of a cluster, we're usually talking beyond redshift 2 or so. And you can see why they're kind of hard to detect and have been. In this kind of simulation, you look at the ancestor of a galaxy cluster, you can see it back even to redshift 6 in the density field, but it gets very spread out, very diffuse. The overdensities get lower. And so you need wide field spectroscopy of faint galaxies, and obviously this is challenging. It's really been on the increase in the last 5 years or so, and it's definitely going to be rapidly increasing in the next 5 or 10 years with the surveys I was mentioning. Nonetheless, even though this is kind of a hard business to find these, there are a few dozen around redshift 2 to 3. So what do we know about the galaxies in them? Have they already started to depart from the evolution that you see in more typical parts of the universe? This is kind of complicated, unclear, and I think depends on what galaxies you're thinking about. So if you kind of focus on what you might call garden variety, normal Lyman break galaxies, you can sometimes see unusual populations in protoclusters. This is a famous example from Chuck Steidel and studying this protocluster at redshift 2.3, where you see this tail of old galaxies. This is consistent with the dark matter halos collapsing earlier in overdense regions. There's some evidence of more star formation, but there's also just a lot of studies with kind of null results. It's not clear that normal galaxies are very different yet in protoclusters. On the other hand, if you look at more rare galaxy populations, there are sometimes huge differences. So this is an example from just last year, looking at the cosmos field, and down in the corner here is a protocluster at redshift 3.4, which is dominated by quiescent galaxies, which are overall like pretty rare at those redshifts and not dominant in most protoclusters. But here's one where it is. Another one was reported just this year. Caitlin Casey has talked about dusty starburst and how they have kind of a weirdly high abundance in a lot of protoclusters. Other very obscure galaxies might be similar. But what I think is striking is that this is probably the best study patch of the entire sky for extragalactic astronomy, and there are huge protoclusters that we're just now finding. So I think it's pretty clear that the inventory is not complete. And so this is one of the motivations for our embarking upon this Lyman-alpha Tomography Survey. We call it LATIS, the Lyman-alpha Tomography IMACS Survey. This is the spectrograph. So this is all being done at the Bada telescope, Magellan, down at Las Campanas. And the overall goal of the project has been to map in 3D Lyman-alpha absorption that arises from the diffuse IGM from redshift 2.2 to 2.8. And we do this by observing lots of UV bright galaxies over an area of almost 2 square degrees. And actually, we started this back in, hard to believe, in 2017, and it's taken about 52 nights, but we've recently just finished the observations last semester. This is building on the first kind of analogous survey called Clamato that was based at Keck. It was the first, I think, to use galaxies as the backlights to measure the Lyman-alpha forest. And it was really interesting. You can see one of their maps here, because it showed that this is a useful technique for finding at least big protoclusters and big voids. The main limitation is just that it's rather small. And so what we've tried to do with LATIS is increase this in volume by about a factor of 10, which is kind of a material difference because it's like finding a few protoclusters versus a few dozen. If anyone here is kind of a aficionado of galaxy surveys, there's some of the details here. So we're using IMACS. It has a wide field of view, so we can observe about 300 galaxies at a time. And that's really what makes this possible and one of the main reasons we started this survey. It's not optimized for blue sensitivity, but you just have such a big field of view that the overall étendue is, I think, is still the best in the world for this until PFS soon. We're covering Cosmos and 2 of the CFHT fields. We go deep for about 12 hours, but we're getting 300 at once, so it makes it worthwhile. And we're almost entirely targeting bright Lyman break galaxies down to about 24.8 magnitudes. We've got about 4,100 spectra now, beyond a redshift of, mostly between redshift 2 and 3, as you can see here. Here they're arranged by redshift and coded by color. So you can see on the right side a lot of interstellar absorption features, and then this is the Lyman-alpha forest that we're mapping with LATIS. So just to give you kind of an orientation of what these far ultraviolet spectra look like, this is an average spectrum. Has a lot of features. Most of the features you see over here arise from the interstellar gas and outflows. There are, however, some that are arising from stellar winds and photospheres that I'll come back to. But what's really the focus of LATIS is the Lyman-alpha forest region over here. So here we're seeing all the foreground absorption. Here are a few of the individual spectra that we get, and then overlaid is a model. And basically, the key quantity that we're measuring and mapping is delta F, which is called the flux fluctuation sometimes. And this is basically the fractional change in the transmitted Lyman-alpha flux through the IGM. But visually on this plot, it's just the ratio between the data and the model, -1. So you can see here it's like completely dominated by noise for individual sight lines. But we have a very high density of sight lines. So by looking for coherent absorption across multiple sight lines, you can start to build up a map. And I'm going to kind of skip the details of how you synthesize a map from these sight lines and just show you the maps. We have a few different visualizations. So here you can see the 3 different fields we've observed, and on the long axis here is redshift from 2.2 to 2.8, and the color here is encoding the amount of IGM absorption. So the red regions have the most, the transparent regions have average or less than average absorption, and you can immediately see that there's a lot of large-scale structure. So there's these huge voids, there's these red clumps that are matter overdensities. They themselves form big structures that go over kind of degree scales in some cases. I find it easier to look at some other of these visualizations. So here you see the same maps, but they're just being projected along one of the dimensions on the sky. So now this is the redshift direction. And the color here is the IGM absorption, and it's being compared to the distribution of galaxies, which are measured at the same time in our survey. So you can see they do, you expect them to trace each other well since they're both tracing the overall large-scale structure. And that is indeed the case. You can see the big void here, for instance, or here that you kind of see in both tracers. There's this huge feature in the middle of the cosmos field that shows up clearly in the IGM and in galaxies. They're kind of complementary structures like this one that you can see traced by both, which I think is quite nice. And then my favorite way to look at the maps is actually by stepping through them in redshift with this visualization. So apologies that the colors keep switching, but now red is regions where there's the most absorption, so the matter density is the highest, and the blue are underdense regions. This is now sweeping through redshift and again showing the 3 different observed fields and the points, again, the positions of galaxies in the survey. So you want to see points clustering with the IGM absorption in the red and avoiding the blue. That is pretty much what happens. We're coming up in the cosmos field on the top now at this really extended structure that kind of snakes over a degree or so. So this is now about halfway through the map. Maybe that's enough to give you a bit of a flavor. So one of the things we quickly realized is these animations look cool, but if you want to actually convert what's observed into a more physically meaningful quantity, then you need to turn to simulations of your survey within cosmological volume simulations. So that's what's needed to convert this delta F that we're mapping out into something like the matter overdensity, or the halo overdensity, or the future fate of the structure, whatever you're interested in. So we've done that by turning both to dark matter simulations and some hydrodynamical ones. We throw down sight lines that mimic exactly LATIS in terms of their distribution and signal noise and resolution and so on. And then we can synthesize maps in the same way. So in this case, this is the observed map, and this is one of the many mock realizations that we can do of the survey. Visually, it looks pretty similar. And that's borne out with the statistics as well. So we want to make sure that the maps are reasonable, that the large-scale structure we're tracing is consistent with LCDM and so on. And that is the case. You can look at the distribution of fluctuations in these maps we've been looking at, or the strength of the maxima of the absorption, or the fluctuations in the galaxies. This is, in each case, the observed survey is black, and this envelope shades the many mock realizations of it we did in the simulations. And it all looks very consistent. So that means, when we look at the maps by themselves, the galaxy maps and the IGM maps, they look statistically as we expect. So the next question you can ask is, what if we compare the structures that we see in the galaxies to what we see in the IGM maps? Do you actually see the same structures traced out in both cases? And one way to quantify this, kind of the simplest way I can think of, is to just count galaxies around highly absorbing regions in the maps. So we call these absorption peaks. They're just places in the maps where there's a local maximum in how much IGM absorption there is. So these should be the matter overdensities, and the horizontal axis here will be the amount of absorption in such peaks. More is to the left, so overdensities are to the left. And for each such absorption peak in the IGM maps by themselves, we can simply count the galaxies in some region around them and measure the overdensity of galaxies. And this is what we found. So every point is an absorption peak, and the solid line here is a trend line, basically. And we repeat the same exercise in all of those mock surveys in big simulations. Now in the simulations, we don't have our observed galaxies, of course. We have dark matter halos. So we need a way to connect our observed galaxies to those halos. And we do that by matching the clustering of the galaxies and the halos, the autocorrelation function, which is kind of a standard technique. And this is what we see for the mock surveys. So these bands are now like 1, 2, 3, and 4 sigma for where this trend line is in the mock surveys. So on the right of the plot, in the kind of moderately absorbing regions, moderate overdensities, everything looks as expected. We find just as many galaxies in those regions as you would expect, and it indeed increases as the amount of absorption increases. There are more galaxies until we get to the left side of the plot, where things really start to break down, which was very unexpected. So these are the most prominent features in our whole map that have the most absorption, should have the most matter overdensity. But we don't see nearly as many galaxies in them as we see either halos in the simulations or even, extrapolating the empirical trend. So, where are these things? We've already kind of seen that a little in the last plot, but this is showing the distribution of galaxies around these absorption peaks in the maps, but now they've been averaged according to the strength of the absorption. So moderately absorbing to highly absorbing. You can see as a function of separation from the peak, the galaxies are distributed around these IGM structures exactly as we see in the mock surveys, exactly as expected, and it really only breaks down in the most highly absorbing places, and it breaks down more as we go toward the center of those. So it's toward the center of the strong absorption peaks where we're kind of missing about half the galaxies we expect to be there from our survey. So another nice thing you can do with the mock surveys is ask about, what are these kind of strong absorption peaks in the IGM maps? And in particular, you can ask what kind of structures they're associated with at low redshift 0, let's say. This is showing the blue curve here, the most massive halo that's formed within these structures by redshift of 0. And when it's above 10 to the 14, we call that a protocluster by definition, basically. And you can see that these strongly absorbing regions, the blue curve, are mostly protoclusters and pretty massive ones too. So, what we're seeing and kind of missing the galaxies from is what we expect to be the centers of very massive protoclusters. So we were excited about this and wrote a paper in Nature about it. I want to just kind of recap the argument because there's kind of a lot of things going on here. So we've made now the largest maps of the IGM on kind of megaparsec scales, these redshifts. We find that their statistics are quite normal. In particular, the number of things that correspond to protoclusters is normal. It's only when we start to count the galaxies in those that things start to look unexpected. And in particular, when we look at the strong absorption peaks, we see only about half the number of galaxies that we expect to be there, either based on the overdensity of dark matter halos in the mock surveys or by looking, extrapolating the kind of empirical trend. So, what does it mean? Are these really protoclusters, or do we trust the IGM maps, or do we trust the galaxy maps, or can we find some way to accommodate both? It's pretty hard to understand how you can get diffuse, widespread IGM absorption and there not be a big matter overdensity there. We haven't figured out a way to do that. It's easy to heat the gas and remove the absorption because it only arises from the neutral gas. But to do the converse and have a lot of absorption but not an overdensity is a puzzle that I haven't heard a solution to yet. So what we think is more likely is that there is in fact a large galaxy population in these regions, but it's just not represented in our survey or basically any other optical survey. And the best way to kind of evade all of the largest spectroscopic surveys, which are the largest ones are all optically based, is just for galaxies to be dim in the rest frame ultraviolet. They can, if they go below our flux limit, then we just simply won't see them. So for that reason, we call these ultraviolet dim protoclusters because we see them in the IGM. We expect there to be a lot of galaxies there that we don't see in a UV survey. So we kind of infer the presence of a lot of ultraviolet dim galaxies. So if this is the case, what are some of the implications? One thing that's kind of striking is that we're observing the best observed fields, and there have been a lot of protocluster searches. So to find a population of really massive ones that weren't found by any other tracer is already pretty surprising. It's also kind of surprising because in order for this to be the case, we need like a large population of galaxies in protoclusters to have evolved quite differently already, in some way that renders them more dim in the ultraviolet. We're not talking about like just a few starbursts or something, but something that affects the bulk of the galaxy population. Apologies. And the other thing that's kind of striking is that if this is true, then we might have seriously misgauged how important the environment was at early times because we just missed the places where it had the most effect because we couldn't see the galaxies, get redshifts for them as easily. So is this actually plausible? It's going a bit out there, I admit, but we should also be kind of humble about our galaxy surveys because we expect in the optical surveys to be missing most of the galaxies at any stellar mass. This is from a photometric redshift catalog, and you can see as a function of the mass, the distribution of R-band magnitude. This is the limit of LATIS, and all other large surveys are kind of in this range. So based on these kind of photometric surveys, we already expect to be missing a lot of galaxies that presumably live in the same mass halos and have the same stellar mass, but aren't represented in the optical surveys. So it's possible that this population that we haven't really mapped out yet could be doing something interesting. So how do we actually verify this? One way is to just get bigger or better IGM maps. This is basically like a 4 sigma result right now, so it's very uncertain in terms of its magnitude. We'll get much bigger maps soon from, PFS will do this. There's a lot of proposed highly multiplex facilities that could also greatly expand the volume, which I'll talk about in a minute. With the ELTs, we'll get better maps with a far higher density of sightlines. But what we can really do now is to take some of these UV dim protoclusters that we see in the IGM maps and try to map them out and find the missing galaxies. That's kind of the ultimate proof. So here's a case study where we started to try to do that. There are these two structures right next to each other on the sky, redshift 2.7. They both have a lot of IGM absorption, similar amounts, similar matter over density as expected. They should both be protoclusters based on the IGM signature. When we look in the galaxy maps, the top one shows up very strongly, just as many galaxies as we expect, but the one on the bottom is totally absent in the galaxy map. So this is like a prototype, kind of an extreme example of the systems that we wrote about in that paper in Nature. So the first thing that we did to try to follow this up, find more galaxies in here, was to go to the radio with ALMA and look at submillimeter bright galaxies to see if there's like a big dusty population in here. So we targeted these galaxies with a line search for CO to find things at the same redshift as the IGM feature. We're still reducing the data to the nth degree, but basically there's nothing really that shows up. It doesn't seem like there's a big structure populated by very dusty starbursts. So the next thing we tried to do to find the missing galaxies was completely the opposite tack and look at very low mass things. And really the only practical way to do that is to find galaxies via the Lyman-alpha emission line, which you can map out using a narrowband filter. And we've started to do that at Magellan, and we can reach down to galaxies that are about 30 times less massive than the ones I've been showing you so far that you see in this map here. And when we look at these low mass galaxies, you see exactly the opposite. So now you see a lot of low mass galaxies in the peak on the bottom, and basically no significant number in the peak on the top. And this is like totally bizarre in this standard picture of understanding protoclusters. Usually the supposition is just that galaxies are in different mass halos, and so they cluster a little more or less strongly. But you shouldn't see drastic differences. And you can't really have like mass segregation on these many megaparsec scales like this. So to me, it really suggests that there still is a significant population that we aren't accessing by these tracers. And ultimately, I think the way to move forward on that is with JWST. You can really get far more complete galaxy inventories in selected regions. And hopefully we'll be able to do that and try to actually locate the analogs of these galaxies, the same mass that must be present in this lower peak. So that was probably the most surprising result we've had so far, that structures can look very different in the IGM and different galaxy tracers, and we may have missed a significant population of them. But there's a lot of other applications of this data set. Let me just share a little bit of the ongoing work. One thing that you can do is to look around the positions of galaxies and measure the average amount of Lyman-alpha absorption. And that's shown in maps like this, which are collapsed from 3D to 2D by showing just the transverse separation on the plane of the sky and the line of sight separation, and the color is the amount of absorption. So if you do this on small scales, you can learn about accretion and outflows, and if you do it on large scales, you're mainly learning about the dark matter halos that these galaxies live in. And this has been done by many people in Chuck's group for quite a while. And what we can do with LATIS is try to do this in a resolved way, where we can look at the halo mass as a function of the stellar mass. And this is still in progress, but basically what we see is something that's quite in agreement with canonical models based on so-called abundance matching, and it's not in agreement with some extreme low mass halos that have been suggested based on galaxy clustering surveys. Well, what I think is kind of a better use of these maps is to turn this around completely. Because we have maps, we can, instead of kind of averaging the absorption around galaxies, we can select different galaxies according to the absorption that surrounds them. This is just illustrating that. I've taken sorted galaxies by how much absorption is around them in our maps into these 4 bins, and then I've just averaged the absorption in the same way as you saw in the last slide. And the point here is just to illustrate that there's a huge range. The same mass galaxies occupy a huge range of large-scale environments, and the maps are good enough to sort them in that way. So that'll be really interesting when we start to compare galaxy properties according to their large-scale environment. NEMA has started to do this in the context of measuring the metallicities of galaxies. So this is a composite spectrum, and you can see that all of the strong features here, which are kind of with the bands covering them, are arising from interstellar gas. But there are a number of weaker features like that you see in red that are arising from the hot stars of these galaxies and are sensitive to the metallicity, and so therefore we can measure the metallicity as a function, for instance, of the mass in the environment. As usual, Chuck did it first in 2016 for kind of a composite spectrum, and then these Cullen and Cascino have come along and done this as a function of mass, and now we're doing that with LATIS as a function of the mass in the environment. And we have a pretty big sample and pretty good spectral resolution to do this kind of thing. And this is what we're finding so far. This is all still in progress, but the metallicity of galaxies seems to increase steeply as you go to higher masses and then hit this plateau where it just kind of stops. And you can interpret this mass metallicity relation with chemical evolution models, and the most important factor seems to be the galactic winds and their behavior as a function of mass. In particular, you can convert this to the so-called mass loading factor as a function of the mass, which relates the outflow rate to the star formation rate. And what you can see is that the mass loading factor kind of plummets steeply until you get to masses around 10 to the 10, and then it flattens out or even starts to turn up again. It's interesting because you see the same thing in cosmological simulations, and there this effect is arising from AGN feedback turning on at high masses. So that could be a signature. That could be what we're seeing, and there are indeed other indications that that's what's happening in these massive galaxies at this redshift. You can also start to extract abundance ratios with the very latest population synthesis models in the far ultraviolet. It has a very subtle effect on the spectra. Here you see the metallicity varying has a huge effect on the far ultraviolet, whereas if you change the alpha to iron ratio, it's extremely subtle, and only in a few places do you see these tiny differences. But with high quality spectra, in principle, you can measure it, and that is what NEMA has done and finds this alpha enhancement of about 0.5 or so. It's roughly in line with what you get from a completely different method of comparing the gas abundance in the stars, because the gas, you're mainly measuring oxygen and iron in the stars. So what this means is that these galaxies have an enrichment pattern consistent with just total core collapse supernova, very little iron contribution from the 1As, and similar to what you see in metal poor stars in the galaxy. You can also look at this in different environments. So NEMA started looking at the metallicities of galaxies around protoclusters. This is a map of the IGM absorption around this set of protoclusters. And here you see the average metallicity of galaxies in different shells centered on the protoclusters. And as you go in toward the central regions, the metallicity turns out to drop pretty significantly, and the star formation goes up a little bit. This is pretty interesting because previously this was only studied in the gas phase, almost only studied in the gas phase, and there was a lot of controversy. I think the kind of latest result that NEMA found is consistent with this, but a lot of prior papers were the opposite, and theory generally predicted the opposite, that there would be more metals in these galaxies. So what we think might be happening here is we're reaching back far enough that we're in the era where galaxies in these overdensities have large amounts of gas accretion onto them that is kind of driving down the metallicities and boosting the star formation. It's only later, once you get a kind of a hot intercluster medium, that the accretion gets killed off and you start to get less accretion and a buildup of the ISM metallicity. So this method has synergies with intensity mapping projects as well. So Maddie Keslu has been looking into this recently in the context of CO map that I guess many of you are very familiar with. It'll be mapping out line emission corresponding to CO around redshift 2.4 to 3.4. And in all of these kind of intensity mapping things, it's very useful to have some other tracer of the large-scale structure that you can cross-correlate with. It helps remove foregrounds like emission lines at other redshifts. It just boosts the signal to noise. And conventionally, you imagine cross-correlating with galaxy surveys. So this shows the signal to noise in COMAP by itself. It's hugely increased when you cross-correlate it with a dense galaxy survey. But what Maddie found is you get almost the same benefit from an IGM tomography survey. That's similar to what Subaru PFS will be soon beginning. And even with very sparse quasar-only surveys, you get a significant enhancement, more in fact than you get from galaxy photometry alone. So this is like another useful tracer that can be used to kind of boost the utility of these surveys if they're aligned in the same fields as the appropriate data are available. Let me just say a few words about where this is going at the end. So this is just one of the, this is the beginning of mapping the IGM in this way, in a sense. We've taken kind of the first step beyond the initial survey, but it's going to explode in volume over the next decade or so. So in the near term, like 2024 to 29, Subaru PFS will construct maps that are similar in quality and sightline density roughly to what I've been showing, but over about an 8 times larger area. This is one of the kind of key projects in that survey. And then there are a number of very highly multiplex dedicated spectrographs that are kind of in developed, being proposed right now, that could expand this to drastically larger volumes, basically, and enable this as more of a cosmological probe. Another thing that we're kind of missing is complete galaxy inventories that we can correlate with these maps to learn about galaxy evolution. So this is one among many motivations for an instrument called the Magellan infrared multi-object spectrograph that we're developing. Nick Conodarius, whom some of you know, I'm sure, is the PI. So this will be a cryogenic multi-object spectrograph in IFU that can go at Magellan. It observes the whole infrared at once at a good spectral resolution. For the MOS mode, you have a pretty wide field of view, like 13 by 3 arc minutes. And the IFU is unusually wide for an infrared IFU. This is seeing limited. It's being designed with high efficiency in mind and also high spectrophotometric precision to do exoplanet work. So if anyone is interested in this, has possible applications in mind, I'd love to talk to you. And looking forward to the ELTs. So this is one area where getting a magnitude more in depth, basically what you get in the seeing limit with the ELTs, is transformative. And that's because we're really on the very steeply rising part of the luminosity function with the galaxies we're observing. So a mag of depth is like an order of magnitude more sightlines. And so that directly translates to a huge improvement in the resolution and the quality of the kind of maps you can make. So in terms of H1 tomography that I've been talking about, you can compare the present to what you could do with the ELTs, and it's hugely different. You can really trace out all of this large-scale structure in some detail. That's not even the most exciting thing. I think the even more compelling aspect is that you have enough sightlines that you can pierce the circumgalactic medium of a single galaxy with a number of sightlines and start to actually get information about the distribution of inflows and outflows around individual galaxies, and that will really be important, I think. And that's, this is deeply connected with one of the highest level recommendations of ASTRO 2020. It's a big part of all the ELT science cases, so I think it's something we'll hopefully be able to do in the next decade or so. Okay, just to summarize here, this is a pretty new technique. And I think it's one that's pretty exciting because it brings a lot of complementarity to the way that we have been mapping the distant universe. LATIS is the largest such survey, but this is a rapidly growing field. There will soon be much larger ones. And what we found so far is that galaxies and the IGM maps kind of track each other as expected most of the time. But there are some interesting exceptions where you see a lot of absorption, and we expect there to be a lot of matter, but they're not very galaxy rich. And so what we think that's pointing to is a population of protoclusters where the galaxy's evolution has proceeded rather differently, and we're missing a lot of the galaxies because they're dim in the ultraviolet. That needs to be confirmed by finding the galaxies. But if it's true, then it's pretty interesting. That means that the early galaxy environments really had more of an effect, and this is kind of a richer phenomenon than you might have expected. And we'll soon have progress from a lot of facilities. I've mentioned PFS. I'll have wide array galaxy surveys, for instance, from Roman, Euclid, and better targeted follow-up from JWST and many other facilities. So we should be able to build up more complete galaxy census and learn more about the connection between these galaxies and the cosmic web. So thank you very much.
Questions for Drew?
Mm-hmm. Yeah. Yes. So the best way to do that, I think, is just with these kind of mock surveys. The good thing is that the diffuse IGM is pretty easy to model, so I think we can do that well. There's some subtleties like contamination from high column density lines and things that are more difficult, but overall, it's a pretty well understood thing, and so I think you can get a pretty good handle on the uncertainties from this kind of approach. And fortunately, it seems that you probably don't need large volume hydrodynamical simulations to do that when we're looking at these core scales, so it's a little more practical to imagine, if you need like a lot of realizations, we have big dark matter surveys, not so much the big hydro ones. So I think it's tractable.
Thank you.
Mm-hmm.
So I'm a little confused about one thing. So you pointed out that the diffusions of Lyman-alpha overdensity which do not correspond to gas overdensity, galaxy overdensity. And is it possible that you have a handful of, say, complementary AGN or a handful of custody stars buried in there which you're not picking up in your UV surveys, but which, if you were to do, let's say, 24 microns or in the hard X-rays, you would pick up, and that would account for the ionizing photon budget to maintain the diffuse AGN?
So if I'm understanding your question correctly, like this could lead to more local ionization. So this goes in kind of, that could definitely be the case, but I think it goes in the opposite direction of what we need. So like that, I think that kind of thing can account for where you find a lot of galaxies and not absorption. The absorption has been erased by the excess local ionization, but to have few galaxies where there is a lot of absorption, I think is what's really tough. It's easy to erase the absorption, but it's hard to produce extra. I think that's basically why. Yeah. There's some exotic possibilities, dark matter models and things, but I think, yeah.
So if I have a follow-up question. Is your proposal then that these UV dim systems in these particular types of protoclusters are like low star formation rate galaxies that for whatever reason are just have star formation suppressed in them, potentially by the environment in which they sit?
Yeah, so we don't know empirically. That's why we just call it UV dim. That's kind of like what's most directly observed. It could be more dust. It could be less star formation. It doesn't have to be extreme because we already know that even in normal environments we're missing a ton of galaxies. So just a little bit might be enough. It is a little still surprising that you kind of see this at this very early stage when the overdensities are really low, and you don't have many of these kind of physical effects that arise in high density media expected to be occurring yet. But I don't think it has to be extreme, like quenched galaxies, for instance, or something like this. It could be pretty moderate, I think.
Was there enough variance in the hydro simulations that you could see this kind of stark difference between some protoclusters having a bunch of UV bright galaxies and a bunch of other protoclusters not?
We don't use the galaxy evolution model in the surveys, actually. We just use them for the IGM and for in halos, because we want to kind of stay disconnected from any particular model of galaxy evolution. But so
it could be something you look at in TNG.
We've looked in TNG, and there's not like such an effect predicted, I guess. I can say that much at least.
Thanks for the talk. This is great. I'm wondering, so you have access to these catalogs, these multi-wavelength catalogs. Have you considered directly cross-correlating with them with like infrared maps, for example? And do you feel like in the infrared you might trace these protoclusters as well if there's like a lot of dust extinction?
Yeah. This is interesting. There's a lot of such maps we can look at. Far infrared maps. There are CMB lensing and a number of and SMG observations and so on, some millimeter. So there's a lot. We've sort of started to look at that. The main difficulty is that when you don't have redshifts, then things get really washed out. We don't have that many. I think if we had like 1,000 of these, then you could probably do that. When you have like 10. Then you kind of really need to know which galaxies are actually in the system with a redshift, and those are like surprisingly sparse for many of these galaxy populations. So I haven't totally given up on it, but I'm a little worried that without more information about the redshifts, it's going to be pretty hard.
You think Mpc-alpha is helpful, like if you're looking at JWST?
Could be, yeah, could be. Yeah, that's a good idea.
Okay, that brings us to 5 o'clock. There's still room for one more person to come to Colloquium dinner for those interested, but if you have additional questions for Drew, we'll do it over wine and cheese. Please thank Drew again.